So welcome to the next lesson in the acids and bases series. This one is on titration calculations. Now that you understand the theory behind a titration, let's find out what we use the titrations for. Our learning objective in this lesson, just one of them, is to be able to perform calculations. We're just going to do two example calculations for the titrations of monoprotic and diprotic acids with sodium hydroxide. So for example, you might get the concentration of and volume of 1 and just the volume of the base, and you'd have to work out the concentration of that base for either a monoprotic or diprotic acid. So our first example is here. Let me read out the question. So we've got the graph on the right, shows the results when 0.5 molar hydrochloric acid was titrated against 35 cm cubed of sodium hydroxide. So you want to calculate the concentration of the sodium hydroxide. And we've got a titration curve given to us there. Okay, so the first thing I think is valuable to do is to write down the balanced equation. And let's write it down in this gap here. So we've got hydrochloric acid plus sodium hydroxide and that's going to give you sodium chloride salt in solution and water. And what you want to do is you just want to notice the molar ratios. So in this case, we see that 1 mole of hydrochloric acid is going to react with 1 mole of sodium hydroxide to give 1 mole of sodium chloride and 1 mole of water. So nice and simple 1-to-1 ratios. That's the first thing to notice. The second thing to notice on the chart is, and you might be given a chart without this helpful dotted line and arrow. What you're going to want to read off the chart is the neutralization point. So at the middle, in the middle point of the vertical section of the titration curve, about there, not always 7 pH, depends on what temperature you're running at, but the middle point of the vertical section, you take the vertical line down from below that to find out the volume, in this case the volume of hydrochloric acid that was added to the sodium hydroxide, and you see that is 25 cm cubed. Okay, so 25 cm cubed. Alright, so let's give it all its names. So that's the equivalence point. We can also call it as the end point of the titration. We can call it the neutralization point, or the neutralization volume. It's slightly better. Neutralization volume. And let's just spend a second thinking about what it is. So, in effect, what it is it's the amount of, in this case, hydrochloric acid that's been added to the sodium hydroxide to exactly neutralize it. So in effect, what you can say is that you've added the same amount of hydrochloric acid that was present, the same number of moles of hydrochloric acid as the moles of sodium hydroxide that you started with. I'll say that again because that's key. All right, so what that volume gives you is it gives you the moles of hydrochloric acid that you've added that is the same number of moles of sodium hydroxide that you started with. Okay, so let's crack on with solving this. And what I like to do is I like to just think about the two reactants here. We've got hydrochloric acid, right, and in the question we are told that we're told the concentration, and we're told that is 0.500 moles per decimeters cubed. And actually from the chart you can see, right, we have worked out the volume for neutralization. That was the 25 cm cubed. So the volume for neutralization was 25 cm cubed of the hydrochloric acid. And the question also gives us some information about the sodium hydroxide. So the sodium hydroxide concentration is the unknown. That's what the question is asking us for. But it does give us the volume, thankfully. So it gives us the volume as 35 centimeters cubed. Now let's crack on with our calculations. And from AS level, you'll remember the formula that is concentration equals moles over volume. And that's what that's the formula that titration calculations use all the time. Okay, so what we want to do is we want to work out the moles of hydrochloric acid because we've got all the information in order to do that. So moles HCl moles of HCl, that's going to equal concentration times volume. And let's just put in our figures. So we've got concentration of 0.500 and our volume is 25 cm cubed. But of course our units of volume in these calculations are dm cubed. So to put it into dm cubed, I'm just going to divide it by 1,000. And if you were to just work through that calculation, we would see that we get 0.0125 moles of hydrochloric acid. That's good. So the next step is to refer back to the balanced equation. So we have the balanced equation here, and we can see that we've added 0.0125 moles of hydrochloric acid, and from the balanced equation we know that for neutralization, because it's a one-to-one relationship between hydrochloric acid and sodium hydroxide, we are going to have 0.0125 moles of sodium hydroxide at neutralization. Okay, so let's just write that in. Moles NaOH equals 0.0125 as well. But remember, the question is asking us for the concentration of sodium hydroxide, and so then we can just remind ourselves of the equation we're going to use. Concentration equals moles over volume. Okay, and we've just worked out the moles, 0.0125, and the volume we were told in the question was 35 cm cubed, but we have to work in decimeters cubed, so we're just going to convert it into decimeters cubed like that, and then we plug that calculation into our calculators, and the answer is going to pop out as 0.357, and its concentration, so the units are moles per decimeters cubed, and that's the answer to the question. So before we carry on to do calculations involving diprotic acids, let's just think a little bit about what diprotic acids are. I'd like to just give you a couple of examples. Let's look at an organic diprotic acid first. Let's look at phenadioic acid. Okay, and so what I want to do is just want to draw the displayed structure. So we've got one of your functional groups coming off the carbon like this, and the other functional group coming off the carbon like that. And so that is ethanodioic acid. Okay, and you might see that written as like that. Just like that. And the other one that you'll be very familiar with is sulfuric acid, H2SO4. And I wonder if you've ever thought about what the displayed formula of sulfuric acid is. Well, here it is. You've got the sulfur in the middle, and two of the oxygens. Let's draw the sulfate first. Two of the oxygens hang off the sulfur with double bonds, and two of the oxygens hang off the sulfur with single bonds, and the hydrogens hang off those single bonded oxygens like that. So we've got our two acid groups on either side of the molecule there. And so when this dissolves and dissociates, then the bonds that dissociate are these bonds here, like that with sulfuric acid. And in the ethanodioic acid, of course, it's these bonds here that dissociate. Alright, so you get your proton or your hydrogen ion going off into solution there, leaving you with a ion that looks like this, 2 minus. You can draw the minuses on either end, or 2 minuses if you drew it differently. And in this case, of course, you've got your SO4 2 minus ion and your 2 H plus ions, both in solution when they dissociate. So that's what diprotic acids are like. They are acids where you get 2 protons released when they dissolve in solution and dissociate in solution. So let's do a titration, or at least draw a titration curve for a diprotic acid and a strong alkali. So as usual in our titration curves, we're going to have pH on the y-axis, and we're going to have volume added on the x-axis. Roughly like that. And we're having the ethanodioic acid in our conical flask, and we're going to add the sodium hydroxide to it. So I'll just write down here volume of alkali added. Okay, so as the titration goes on, this is what the curve is going to look like. We're going to start at a low pH because we've got just acid in our conical flask. Alright, and then we're going to see a quick first neutralization, and then we're going to see a second neutralization before it levels off finally. And so let's just consider what's going on here. So at this point here, this is our first neutralization point, or our first equivalence point. It's at about pH 2 or 3. Let's say let's call it 3, and it corresponds to the loss of the first proton. So if you remember, our acid looked like this. So in this neutralization reaction, what's happening first is this proton is removed and is going to react with the alkali, and in the neutralization of that proton is what is given here as our first equivalence point. So let's label that first equivalence point. And then what happens in the second one, I'll draw that in a different colour. So this neutralisation point, this equivalence point here, right, our second equivalence point, let's call that at pH, let's call it 8 or 9, let's call it 8, alright, corresponding to the middle of the vertical section, and that's our second equivalence point. And that corresponds to the loss of this proton here, which then reacts with some more alkali and is neutralized. So let's just list out the two equations. Go back to blue to do the first one. So for our first equivalence point, we've got the acid molecule in its entirety, like that, and it's reacting with a hydroxide ion from the sodium hydroxide, and the first hydrogen stays on the acid molecule, but the second one is lost, but the electron is kept by the oxygen, and the hydrogen ion floats off as we drew in red, and that's going to react with the hydroxide ion to make a water molecule. So that's our equation for the first equivalence point. And then for the second equivalence point, what we have is this molecule here is the molecule that's now reacting. Sorry, not that one, this one here, I'll draw it. This is the one for the second equivalence point. Okay, so we're starting off with that molecule, or that ion rather, sorry. And it's going to lose its second hydrogen ion, and that hydrogen ion is going to break off and react with this hydroxide ion here, and so we're going to be left with double negative ion, and the hydrogen ion that's been lost is reacting with that hydroxide ion to make another water molecule. So there's our two equations for our two equivalence points for a diprotic acid and base titration. So lastly, let's do a calculation with a diprotic acid, and we can stick with ethanodioic acid. And we're told in the question that we have 25 cm cubed of ethanodioic acid, and that's completely neutralized by 20 centimeters cubed of 0.1 molar sodium hydroxide. And the question wants us to calculate the concentration of the ethanodioic acid. So let's write down what we know, as we have done before. First of all, we want the balanced equation. Alright, so we'll start off with ethanodioic acid, and instead of writing the displayed formula, we can just write it as C2H2O4, and we're reacting that with sodium hydroxide. And that's giving us the salt that's written here. And 2 waters. Now I've left a space here just to remind ourselves of a point. So we have 2 hydrogens in this acid that are dissociating, and so that what that means is that it's going to take 2 moles of sodium hydroxide to neutralize every 1 mole of ethanodioic acid. Right, so we're going to put a 2 in here, and now you can see that that balances. So in the salt, we now have, instead of the 2 hydrogens, we have the 2 sodiums that have taken their places, and the 2 hydrogens from the acid have reacted with the hydroxide ions of the sodium hydroxide to make our 2 moles of water. So if we understand the reaction, we can carry on. If you don't understand that reaction, then pause, go back, have a look at it, and then we can carry on with the calculation. So let's write down what the question tells us. Firstly, let's list out what we know for ethanedioic acid. Okay, so it tells us that we have a volume of 25 cm cubed. And it doesn't tell us the concentration, but it tells us some information about the sodium hydroxide. What does it tell us? It tells us the volume. It tells us that the volume is 20.0 cm cubed. And it also tells us the concentration. It tells us the concentration is 0.1 moles per dm cubed. Okay, so I'll do the calculations in blue. So the first thing we can do, of course, is we can use the 2 bits of information for sodium hydroxide to calculate the moles as usual. So the moles of sodium hydroxide from our usual calculation is going to be concentration times volume. I'll write it out just for completeness sake. Concentration times volume, and our concentration is 0.1. And our volume in decimeters cubed is going to be 20.0 divided by 1,000. And so when we work that out, of course, it's going to come out at 0.002 moles. Quite conveniently. Okay, so now I'll change colours because we're just moving a step forward in the calculation. So we're going to refer back now to the balanced equation and to remind ourselves that we need 2 moles of sodium hydroxide to react with each 1 mole of ethanedioic acid. So then we can then say that the moles of acid is going to be half, in this case, the moles of sodium hydroxide, because of this 1:2 relationship here. So the moles of acid that we need is 0.001 moles. Right? For every 1 mole of acid, we need 2 moles of alkali to neutralize it, because it's a diaprotic acid. So now we have the moles of the acid, and we also have the volume of the acid. So now we can calculate what the question is asking us for, which is the concentration. And the concentration, you'll remember, it is moles over volume. And the moles is 0.001, and the volume is 25 cm cubed, but of course we deal in decimeters cubed, so we're just going to divide that by 1,000. And so when we put that into our calculator, or in this case we'd be able to do it in our head, we can see that the concentration is going to turn out to be 0.04, and let's give it to the right accuracy, 0.0400 moles per decimeters cubed. That's what the question's asking us for. As usual, let's just check that we've met our learning objective. And so have we performed calculations? Are we able now to perform calculations for the titrations of both monoprotic and diprotic acids with sodium hydroxide? Well, you remember we did the monoprotic acid we used was hydrochloric acid. We titrated that with sodium hydroxide, and the diprotic acid that we used was ethanedioic acid, and we titrated that also with sodium hydroxide. So I think we can give ourselves a tick for that learning objective.